These are the pre-calculus frequently asked questions for section 5.5. Most of these are going to come off of the 5.5 day 2 assignment. Number 41 says reducing air resistance. A 4-foot airfoil attached to the cab of a truck reduces wind resistance. If the angle between the airfoil and the cab top is 18 degrees and angle B is 10 degrees, find the length of a vertical brace positioned as shown in the figure. Vertical means up and down. So I've got this triangle formed for this airfoil, and I know that this is 4 feet. And I know that this has been broken up here, and they said this was 18, and in the information that they gave us, it said angle B is 10, so I'd have to slip a little 10 degrees in there. Well, that information is enough for me to figure out what that vertical up and down distance is, because now I know this is 28 degrees. And now I could just use some basic right triangle trigonometry here. But that's kind of a goofy picture, and without knowing what on earth it is they're talking about, it might be hard for you to get this one going. It's this piece up at the top of the tractor trailer there that we see that's called the airfoil. And the reason that that's going to reduce that air resistance is because as the truck drives, if that foil weren't there, the truck would just be a normal cab, looking something like this with the windows, and the air would hit against the trailer, and that would give air resistance, wind resistance, as it's moving. So what they've done here is created a situation where if the air hits, because of the airfoil, it's going to get pushed back and over the top of a tractor trailer. And this is something they used to do a lot when gas was really, really high priced. You still see these a lot nowadays, but when gas had first increased immensely in cost, people were getting these a lot on their tractor trailers. So anyway, I probably better go ahead and find the answer for you here. This would be the distance that we are looking for. So this is opposite and hypotenuse. The sine of 28 degrees equals x over 4. 4 times the sine of 28 degrees equals x. And then we just grab a good old handy-dandy calculator, and this one comes out to 1.8778. So 1.878 feet. And yeah, you could always take that times 12 and convert that into inches too, but the book gave the answer in feet. Number 43 says, finding height. 2 observers are 600 feet apart on opposite sides of a flagpole. And it says the angles of elevation from observers to the top of the pole are 19 degrees and 21 degrees. So here's what I know already. They are not equal distances from the base of the flagpole. If they were, those angles of elevation would be the same. This would be an isosceles triangle, but it's not. So what to do now? Well, if I can figure out one of the sides of the big triangle, then I could use that as a hypotenuse and use sine in order to figure out what that height is. So I think I'm going to go after this little bugger over here and figure that out. So I would set this up using the law of sines because we do have an angle-side angle relationship. So the sine of 21 degrees over b equals, and then you realize, wait a minute, I have to find the other angle. Well, it's not going to be too hard to do. We know every triangle has 180 degrees. So if we take 180 minus, well, we have 19 and 21, that's going to add to 40. So this is going to be 140 degrees. So we set this up, and b will equal 600 times the sine of 21 degrees divided by the sine of 140 degrees. And that will come out to about 334.513 for B. Now, I'm going to keep that in my calculator, have it all there perfect, so I can use it for the next calculation, but I'm going to go ahead and draw this up here, write it up here for you. So you can see that now I could use this triangle, because this is a right triangle with some basic right triangle trig, and say, Here is opposite, here is hypotenuse, that is sine. So the sine of 19 degrees equals h over our very wonderful 334.513. We would multiply both sides by our 334.513, which is still stored in our calculator perfectly. So you just need to put times sine of 19 degrees. And we have 108.907. And let's see, were there units here? That was feet. So there it is. So law of sines, since we had an angle side angle relationship, and then just using a basic right triangle trig equation there, SOHCAHTOA action. 46, I could see why this one was messing with people. First of all, there's a lot of reading, and there's a lot of data, and you know, those two things tend to turn people off. So a geometry class is divided into 10 teams, each of which is given a yardstick and a protractor to find the distance from a point A on the edge of a pond to the tree at point C on the opposite shore, and there's a picture down below here of what's going on. After they mark points A and B with stakes, each team uses a protractor to measure angles A and B and the yardstick to measure distance from A to B. Their measurements are given in the table. Use the data to find the class's best estimate for the distance AC. So here's a little problem stats. You have to think, what would be the best estimate? We can't just say, oh, I like this one, I'm going to use this one. Well, with all of this data, you'd have to determine whether or not you should be using the median, the mean, what should you use for this? And the absolute best thing to do in this situation where there are 10 pieces of data is going to be to go ahead and find the average. And so what you do is you take all of the entries in angle A and you add all of those up and then you divide by 10. And we get this, 79.7 degrees. So that would be what you would use for the measure of angle A. You do the same thing for B. Add up all 10, and we get 839. And there were 10 entries, so we divide by 10, and that gives us 83.9 degrees, of course. And then all you would have to do is subtract from 180 to get the measure of angle C. So the measure of angle C is going to be 16.4 degrees. And then you take a look at the lengths. And this is probably where people started to get all messed up. We've got feet and inches. And so what you want to do first is figure out, well, how many inches are we talking about here? Because maybe it'll work out to something really nice in feet. So you just take 4 plus 5 plus 0 plus 1 plus 11 plus 3 plus 5 plus 8 plus 4 plus 7. And that very nicely turns out to be 48. And 48 divided by 12 would be 4 feet. 4 feet in inches. And then you'd go ahead and add all 10 of these feet pieces of data together with that 4. And then you go ahead and divide by 10. So we get an average of all of that of 25.9 feet. So pretty obviously that was going to be 259 divided by 10 when you add all of that up. So there's our average, and now we would have an angle-side angle relationship. And yeah, that's kind of a small drawing down there, but notice at this point, we know that this is 79.7 degrees here for A, and we know that B is 83.9 degrees. We know that C up here is 16.4 degrees, and we know that this is 25.9 feet. And what they wanted to know was how far it was from A to C, so I just popped a little B on that initial drawing over there. And then we just use the law of sines, because we definitely have either angle side angle or angle angle side, depending on which way you want to look at this here. But the given information for A and B probably fits better with that angle side angle information. So then we set up our law of sines proportion. Sine of 83.9 degrees over our little b equals the sine of 16.4 degrees over 25.9. So So little b is going to equal 25.9 sine of 83.9 degrees all over the sine of 16.4 degrees. And that comes out to be 91.214 feet. So I do know a few pre-calculus students have signed up for AP Stats next year. And this is a good problem to kind of lead you in that direction where you have to think, what is my best measure of central tendency? And that's where you choose between mean, median, and mode. Notice I didn't even talk about mode earlier because often that's the worst of those three measures of central tendency. 47, true or false? The ratio of the sines of any two angles in a triangle equals the ratio of the lengths of their opposite sides, and justify your answer. Well, that sounds good. So let's see here, the ratio of the sines. Wait a minute, that's like sine A over A equals sine B over B. So what they want us to do is show that when you have the sine of A over the sine of B, that's going to equal A over B. Cool, let's just cross multiply. A times the sine of B equals B times the sine of A, and then work to get the sine of A and sine of B together. Divide by the sine of B, and we have A equals B sine of A over sine of B, and then we would go ahead and divide both sides by lowercase b. And there it is. This is true, and there's our justification. So they're just having us manipulate the law of sines a bit here. If the whole thing was kind of messing with your head a little bit at the beginning, what you might want to do is start off, especially if this were to happen on a test, start off with a really basic triangle, one that you know a lot about, like this one. I mean, that's just a basic famous Pythagorean triple there, 3, 4, 5. And you'd say to yourself, all right, here's what they're really saying. They're saying if I take the sine of angle A and the sine of angle B, and I look at their ratio, if I divide them, that's going to give me the same thing as A over B. Oh, let's take a peek. So here's a little C. So if we want the sine of A, the sine of A is going to be 3/5. And if we want the sine of B, that's going to be 4/5. So that would be 3/5 multiplied by the reciprocal of 5/4, which is 3/4. Trying to give us another way here that we can understand why the law of sine works, why those laws that we're talking about right now, law of sines, work at this time. 53A says, show that there are infinitely many triangles with angle, 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 given if the sum of three positive angles is 180 degrees. What I'm going to try and do is talk you through this in terms of some of the things that you learned in geometry. So if we have the sine of A over A equals the sine of B over B equals the sine of C over C. And they're trying to say that we're supposed to explain why this is always going to work. If you use this angle, 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 which means all the angles are going to be the same. And if you start thinking about that, you realize, well, their angles could be the same, but they definitely could be different sizes. So what we're really trying to do is explain why changing the sizes of this ratio is not going to affect what we see here. And if you remember, what we would do when we were talking about that similarity is we would talk about a scale factor. Scale factor of k. And what they're saying here is, what we're going to do is we're going to change the size of those side lengths by the same amount. And when we do that, our ratios are still going to work. So what I'm going to do here, just to make this easier to see, is I'm going to say my scale factor is 1 over k, because obviously if I want k to be 1/7, I can make k equal to 7. And if I want k to be an integer, that's going to be greater than 0, I could just go ahead and put a fraction in for k and say k is 1/3, and that would make it a 3. So this would cover all the situations of scale factors that we would need. But what I do to one piece of this algebra, I have to do to all. So the sine of A over Ka would equal the sine of B over Kb, which would equal the sine of C over Ck, Kc, either way. I guess I had the K first and the other two. So what we've done is we have taken a scale factor and we have multiplied it times our law of sines formula. And it's going to work. I mean, it's going to be the same ratio of the sides no matter how you do that. So when it says show that there are infinitely many triangles with angle, angle, angle given if the sum of the three positive angles is 180 degrees, I would just say use a scale factor of K to all three parts of the law of sines. So using a scale factor of K to all three parts of the law of sines gives an equivalent. Suppose I should put this gives an equivalent ratio. And there it is. So yeah, it's kind of a little challenge problem there where you're thinking about how does all of that make this happen. Then B, part B. Part B said, give 3 examples of triangles where A would be 30 degrees, B would be 60 degrees, and C would be 90 degrees. Well, we've really got an endless stock of these because they're infinite. But what we would want to do is say, you know, basic 30, 60, 90 triangle, we have 1, 2, and the square root of 3. So all I need to do to get one that would be similar to that is just pick a number to multiply all the sides by. If I multiply all the sides by 2, I still have a 30, 60, 90 triangle. And if I multiply all of those sides by 3, so now I have 2 times 3, which would be 6, 4 times 3, which would be 12, 2 square roots of 3 times 3 would be 6 square roots of 3. That relationship that they have of the short side being 1, the hypotenuse being 2, and the longer side being x square roots of 3, whatever that short side is, times the square root of 3. Those are all 30, 60, 90 triangles. And then part C says, give 3 examples where A equals B equals C equals 60 degrees. Well, 60 degrees for all 3 angles would make them equilateral. Equiangular and equilateral. So we just come up with any 3 triangles that have all 3 sides the exact same length. I think because you got a little stuck on A on this one, you maybe did some overthinking in B and C, or maybe it was just part A that was all you needed. But those are the FAQs that you asked for.